Hello everyone. We want to discuss the intersection of three planes in this lecture. When you have three planes in total, there are eight possibilities. Like three planes can have eight scenarios happening in terms of their intersection. So perhaps one case is where the three planes are parallel and distinct and no plane intersects the other plane at all. So this could be like one scenario, for example. Obviously, we know that the three vectors would be collinear. The three normal vectors of the three planes will be collinear because the planes are parallel. Or it could be the case that plane P2 and P3 are coincident and plane P1 is parallel to those two planes, but parallel and distinct. So that could be a second scenario. We can have a situation where all three planes P1, P2, P3 are exactly one on top of the other and all three planes are coincident. That would be a third case scenario. We can have some sort of intersection happening. You may have two planes parallel and distinct and a third plane intersecting those two parallel planes. This could be like a fourth case scenario where you can say two of the planes have collinear normal vectors, but the third normal vector is not parallel to the other two normal vectors of the two planes. It could be that the two parallel planes are actually coincident and they're intersecting the third plane. So that would be like a fifth case scenario right there. Or another situation with three planes could be a situation like this, that we end up with a triangular prism. So three planes are intersecting one another such that we have one, two, three lines of intersection, and they make a shape that looks like a triangular prism. Okay, the three faces of a triangular prism, if you see, they are mutually intersecting at a line, which is the edge of the triangular prism, basically. But that is like a scenario for itself. That's number 6, you can say. Another situation with the three planes is just like the pages of your textbook. So there are three planes here that they're intersecting at one common line of intersection. This could be a seven, you know, case of intersection of three planes. And finally, if you look at the corner of the room you are right now, if you look at the corner, you will see two walls and one floor. So you see that there are three planes that are intersecting at one unique point of intersection, which is the corner of the room you are right now in. The three normal vectors, none of them are, of course, collinear to one another. So this could be the eighth scenario when we talk about the intersection of three planes. So in general, there are eight possibilities out there. Here we have a numerical example. We have three planes, and we want to know if they're going to intersect um, at a unique point of intersection, or they're parallel, or what's the scenario. End of the day, it has to be one of those eight possibilities that I discussed. So quickly, if I find the first normal vector, 1, 3, negative 1, and this one would be 1, negative 1, 1 again, and this would be 1, 2, 4. When you look at these normal vectors, it is very clear that not two of them are collinear to one another. So it's not these kind of scenarios where the three planes are all parallel and distinct, because if that was the case, then the normal vectors of the planes would be parallel and the vectors would be collinear, but it is not the case. So we have to forget about that possibility. And even two of those planes are not parallel and distinct, I can tell, because not any pair of normal vectors are collinear here either. So forget about all of those. It could be like this scenario here. It could be the triangular prism scenario, or it could be like the textbook scenario, or maybe it is this scenario where the three planes are actually intersecting at one single point. And To figure this out, we can do one thing. We can check to see if these normal vectors are collinear or coplanar or not. Okay. Now, why? Because if you think about this scenario, for example, if you look at all those normal vectors, one of them could be this, one of them could be that, one of them could be this and that, and it's hard to show. It could be this, okay? These three normal vectors are actually coplanar. They can lie on a plane, all right? For this scenario, again, we can have a normal vector like this, a normal vector like that, and another normal vector like that. And these three normal vectors that are perpendicular to the three faces of the triangular prism, they are also coplanar vectors, okay? But that is not the case for this situation. So if you look at the corner of your room, there are three planes intersecting at the corner of the room, point of intersection, and those normal vectors of those three planes are not coplanar. They look like this. If I can show it, they look like this. See, they're not coplanar. They're not located in the same plane as the case was in this case. For this case, it was like this. So for these two scenarios, the normal vectors are lying on the same plane. They're coplanar. But for that scenario, it's not. So if I somehow figure out if these three normal vectors are, let's say, not coplanar, then I would be omitting these two scenarios, and automatically I would know that these three planes must be intersecting at a unique point of intersection. But if they were actually coplanar, then I would be saying that this situation is out of discussion. It could be either this or that, all right? And in that case, I have to see if by solving the system of equations, the system of equations does have solution or not. If we did have a solution, it would be, of course, this textbook scenario. If we didn't have solution for the system of equations, it would be the triangular prism. But for now, I just have to figure out if these three vectors are coplanar or not. And how do we do that? We use the triple scalar product. We know that if the triple scalar product of three vectors is 0, it means that they are coplanar. So I'm going to find n1 dot n2 cross n3, and I'm going to check. Okay, I'm not going to say it's 0 yet. I'm going to check to see if it is 0 or not. Okay, if it is 0, then the three vectors are coplanar. So I have to do n2 cross n3. So 1, negative 1, 1, 1, negative 1, 1, and 1, 2, 4, 1, 2, 4. We are finding the cross product of the vectors. So negative 4 minus 2 is negative 6. 1 minus 4 is negative 3. And 2 plus 1 is 3. So this is the cross product of vectors n2 and n3. Okay. Now I find the dot product of n1, 1, 3, negative 1, with this vector I just got, and now we just have to see what we get. So we get negative 6 minus 9 minus 3, and that is not equal to 0. Okay, so that is not equal to 0. And what does that mean? If the triple scalar product is not equal to 0, it means that the three vectors are not coplanar. And if they're not coplanar, which means it's not this case or that case, then automatically it has to be that case. So with these calculations right now, we could figure out that if this system of equations is going to have a solution or not. Now I can tell it does. So I would say three planes intersect at a single point of intersection. Okay, so note that I have not even solved the system of equations yet, but I do know that these three planes must be intersecting at a single point of intersection. So we're going to see if this is true or not. Okay, so by numbering the equations, equation 1, equation 2, equation 3, if I just add the first two equations, negative z plus z will cancel out each other, and I can eliminate the z unknown here. So add them up. So 1 plus 2 gives me 2x plus 2y minus 2 equals 0. Okay, simplify x plus y equals 1. So this is one equation, number 3 I got. So I eliminated z between the first and the second equations. Now I'm going to eliminate z between the first and the third equations. So I'm going to add 4 times the first equation so that I generate negative 4z. I'm going to add it with the third equation. So we get 4x. So let me write 4x plus 3y, 12y, sorry. 4x plus 3 times 4, 12y, minus 4z plus 36 equals 0. I multiply the equation number 1 by 4, and equation number 3 was already x plus 2y plus 4z minus 5 equals 0. So now if I add these two equations up, I get 5x plus 14y, these two cancel out each other, plus 31 equals 0. So from here, I'll end up with 5x plus 14y equals negative 31. Okay, so I eliminated z between the first two equations, and then I eliminated z between the first and the third equations. You can choose to eliminate any of the three unknowns x, y, z, and you can choose any pair of equations. So that's what I did here. So now equation 3 and equation 4 gives me two equations and two unknowns. So I'm going to rewrite them. So that is equation 3 and equation 4. Okay. So now I can use substitution elimination methods traditionally. So y is 1 minus x. So 5x plus 14. Instead of y, I substitute 1 minus x. You learned this in grade 10 math. So 5x plus 14 minus 14x equals negative 31. So do the math. 5x minus 14 is negative 9x. And negative 31 minus 14. So that would be negative 45. And the x would be 5, because 5 times 9 is 45. So I found x. I substitute back in equation 3. So sub into 3. So from there, y is 1 minus x. So 1 minus 5, that would be negative 4. So as you see, I found value of x, I found value of y. This is called method of elimination. Okay, there's other ways of solving systems of equations. That's matrix methods, Gauss-Jordan method, which you may study if you want. And now we have to find the value of z. So I have to sub in one of the first three equations. I select the second one, okay? So sub into equation number 2. So imagine if I had not numbered the equations, you would be confused. So it's a good idea that I numbered every single equation here. So x is 5, y is negative 4, and we are solving for z now, okay? So that's going to be 9 minus 11 equals negative z. So from there, z would be, of course, positive 2. So we found the point of intersection. This point of intersection, I call it point A, has an x coordinate of 5, y coordinate of negative 4, z coordinate of 2. And this matches with our prediction that we had before. So we did a collinearity check. We made sure that the vectors are not collinear. And after that, we did a coplanarity check to make sure that the three vectors are coplanar or not. And we figured out that vectors are not collinear. So 3 normal vectors are not, coplanar. Yes. So that was the conclusion we came up with after the triple scalar product was not equal to 0, because -6 minus 9 minus 3 is never equal to 0. And therefore, we concluded that the three planes must be intersecting at one point of intersection, and that's this scenario over there, like the corner of the room. And we knew that if we solved this little equation, we would end up with one unique solution. And when we solved it by using the elimination method, we ended up with the coordinates of point of intersection to be 5, -4, 2. That's the coordinates of that unique point of intersection. So I hope you understood how we solve systems of equations by elimination, and how we narrow down our search to find out which scenario are we dealing with when we are given three equations of a plane, what is happening there, and how we can distinguish all these 8 different cases with respect to one another. Thank you for your attention.